In this video, we're going to look at using the formula 1/2 AB sin C to find the area of a triangle. Let's start off with three different triangles. I'm going to have a right angle triangle, I'm going to have an isosceles triangle, and I'm going to have a scalene triangle. If we can find the base and a perpendicular height for each of these triangles, we can use the formula the area is equal to the base multiplied by the height divided by 2, or we could write that A is equal to 1/2 base multiplied by height. So if I put some dimensions on, let's go ahead and put some dimensions on. We'll put now this base here and then we'll have a height. And let's say now that the base of this one was going to be, we'll say that that's going to be 10 meters. So put in the 10 meters on, that is 10 meters. And then I'm going to say now that the height, let's say the height is 7 meters. To find the area, we would simply do 10, that's the base, multiplied by 7, divided by 2. We divide by 2 because, of course, this is half of a rectangle. So I can say now that the area is going to be 70 over 2, so that's 35, and the units will be meters squared. So nice and straightforward. I can do that because I have the base and a perpendicular height. If I look at the next one, I can use this formula if I've got a base and a perpendicular height. So the perpendicular height would be here, or we could draw it to the side, and then we would have the base. If we had the slant height, we could use Pythagoras, but in terms of this, straightforward, let's say that that is going to be 5 millimeters, so let's go 5 millimeters, and the base is going to be, we'll say that that's going to be 4 millimeters. So all I'm going to do now is say that the area, and I'll use this particular approach now, is going to be 1/2 of the base, which is 1/2 times by 4, times by the height, which is 5, and that is going to give us on there 10, and it will be millimeters squared. So the area is 10 millimeters squared. So all I've done is found the base and the perpendicular height. Remember, perpendicular means at right angles. So as long as these are at right angles, we can use this formula. If I look now at this one just here, let's go ahead and put a base on. So that would be the base, and then our perpendicular height would be this length right here. So if we had on this one, let's say that this height here, we'll say that this is going to be 6, and we'll go for 6 centimeters. And we'll say that this one is going to be 7 centimeters. Let's put that on. All we would say then is that the area was going to be equal to 7 multiplied by the 6 divided by 2. So the area is going to be 21 centimeters squared. So nice and straightforward, and we've just plugged them in. If we look now, we've got to find the area of each of these triangles. So with all of these now, it looks as if we've got a base and a perpendicular height. So if I went ahead, I could say now that that was the base and that is a perpendicular height. So it doesn't necessarily have to be a right angle triangle. Base and then the perpendicular height. If we look at this one, we've got the base now and the perpendicular height just here. So it's nice and straightforward to work out. That one being a right angle triangle, we assume it is. We would just do the base times height divided by 2. So there's the perpendicular height, there's the base. This one right here, we've got the base, which is 1.8, and the perpendicular height. The question then comes is, what happens if we don't have a perpendicular height? Well, let's go ahead and model that situation up. What I'm going to do is take some triangle, and we'll just do something like this. Let's just put this on. So this now is a scalene triangle. So it's not right angle. It might look, I mean, if we really wanted to, we could certainly make it not look like a right angle triangle if you're concerned that that is a right angle triangle, and we'll do something like this. So what we've got then is our triangle, and we can put on some side lengths. So what I'm going to do is say that this one right here, we'll call this one A, so that'll be side length A. This one is going to be B, and this one is going to be C. If this now is C, we can say that this is going to be the angle big C. So capital C, lowercase c. If I wanted to work out now the area of this triangle, what I would need is the base and the perpendicular height. So let's just say that A was the base, and what I'm after here now is a perpendicular height. So if I can drop a perpendicular down here, then we can go ahead and look at finding that particular height. So if I just straighten that up a touch, that looks about right. And how I'm going to do this is to form a right angle triangle. And the right angle triangle, if I just draw it now, is going to be here. So I'm going to take this as the right angle triangle. If I can find this perpendicular height, which I'm going to call h, then we can simply use the base times by this height divided by 2. So if I look at that, I can say now that this is going to be h. At this stage, what I'm going to do is use basic trig ratios. So the trigonometric ratios, SOHCAHTOA. So my little sketch here, let's go ahead and put the sketch. So my triangle looks something like this. So I've got now on here an angle, and my angle is C. I've got a hypotenuse of B, and I've got an opposite of H. So we've got C here, we've got lowercase h, we've got now B. This is the hypotenuse, this is the opposite. We can find this height by finding the opposite of a right angle triangle. So if we go back to our right angle triangle work, we know that if I've got the opposite and the hypotenuse, we would use sine. I want to find now the opposite, so it's going to be the sine of the angle multiplied by the hypotenuse. So what I can say is that the opposite, which is h, is the sine of c multiplied by the hypotenuse, which is b. So I can say now the following, that h is b sine c. If we just leave that there for now, I can say if I had this triangle right here, the area now would be 1/2 a, which is a base, multiplied by the height. I'm going to put therefore, so using my therefore symbol, the area is going to be 1/2 a. Instead of h, we're going to have b sine c. This formula is given in the exams. So that shows how it works, and all I'm going to do is give you a nice little picture to remember this. So what we're going to have is something like so, and this is our triangle. We're going to have now the angle, so this is going to be C, so the angle is here, that's C, this is going to be A, this is going to be B. We can say that the area of this triangle, where we have the enclosed angle C, it's enclosed between B and C, is 1/2 AB sine of C. So all you need to do is stick the numbers in and you will solve the problem for the area of a triangle. You can of course still use base times height divided by 2 if you have a perpendicular height. So let's go ahead and put this into action and look at solving some problems. We're asked to find the area of the shaded regions in the following figures. So all we've got here is a nice straightforward triangle, and I'm going to label these up. So I'm going to say that this is going to be the side A and this is going to be the side B. It doesn't matter which I call which, and this is going to be the angle C. So we can say now that the area will be 1/2. We're going to have A, which is going to be 4, multiplied by B, which is going to be 5, multiplied by the sine of 26 degrees. We do need to check that our calculator is in degrees mode, and some questions will want you just to tidy this working up to gain full marks. So 1/2 of 4 times by 5 is going to give me 10, so 10 lots of the sine of 26 degrees. So in the calculator, shift mode 3 if you're unsure. You should have a little d there for degrees, and we need 10 lots, and I can just type it in as 10 sine of 26. I don't even have to close that off if I'm being lazy, and we can say that the area is 4.39. So the area, so let's write this in, the area is going to be equal to 4.39. That will be centimetres squared, and that's given now to 3 significant figures. We're not asked for a level of accuracy on here, so I'm just going to go ahead and write it like so. If we look at the next one, it might help you if you wanted to turn it round. I don't think we need to, we've got C, we've got A, and we've got B. In this particular case, A is equal to B, and we will see that this problem occurs often when we're looking at triangles within circles. So the area is going to be 1/2, then we're going to have 11 squared, or I can write 11 times by 11, multiplied now by the sine of 5 degrees. So straight through a calculator if you like, so you can say it's going to be 121 over 2. If you wanted to write that, what's that going to be? 110.5 times by, 121 over 2, 60.5 if you wanted, multiplied by the sine. I'm just going to put it in as 0.5 times 11 squared multiplied. And I'm just looking at different ways that you could write this in. Different people like to do different things. That would be perfectly fine. And that's going to give me 5.27. So 5, and I'll put this is 5.27. That is centimetres squared. And again, I've rounded that to 3 significant figures, or in that particular case, 2 decimal places. So nice and straightforward. This one right here, we'll just write it out quickly. It's going to be 1/2. We're going to have 9. We're going to have 7. And we're going to have the sine of 130 degrees. And that will give us exactly what we need. Okay, let's look at some more. It says in questions 1 to 5, calculate the areas of these triangles. So in triangle ABC, angle ABC is 61 degrees, AB is 6 centimetres, and BC is 8 centimetres. So what I'm going to do is just sketch this up. So I'm going to have, and we only need 2 side lengths here. I'm not even going to put the third one on, as once we have 2 of them and we have the angle, we've defined the bottom one. So this right here is going to be my angle. I'm going to say that this is A, I'm going to say that this is B, and this one is going to be C. So A to B is going to be 6 centimetres. We've got now B to C, which is going to be 8 centimetres, and we have the enclosed angle. Remember, if it's the angle ABC, it's B in the middle, that is where it's at. So we have 61 degrees. So we can say that the area is going to be equal to 1/2 multiplied by 6 multiplied by 8 multiplied by the sine of 61 degrees. So if you wanted to tidy that up, 1/2 of 6 times by 8 is 24. So 24 sine of 61 degrees, and that can go straight through a calculator. So 24, and if you do want to still press for multiply, you can do. On this one you don't need to. If you want to close the bracket off, you can do. You don't need to. And that's going to give us 20.99 and so on and so forth. So I'm going to say that the area is going to be equal to 21.0, and that will be centimetres squared, and that's given to 1 decimal place. We could do some more of these if you wanted to look at them. Look at this one just here. We've got X, Y, and then Y, Z. So a quick sketch up now. It's going to look something like this. It looks something like so. And again, you might want to define the third length. I'm just not massively fussed about that. So what I'm going to have then is that we're going to have X just here, we're going to have Y just here, and we're going to have Z just here. So this is the 8.5, this is the 13, and then the angle is going to be here, which is 77. So once we've got now this angle and these 2 lengths, remember we don't really need, we can of course put the line XZ on there, but it's going to be defined anyway, that won't change. So with this one, all we would do now to find the area is 1/2 multiplied by 8.5 multiplied by 13 multiplied by the sine of 77 degrees. And we can put that through a calculator and get our answer. Remember, this formula is given in exams. It will always be written that the area is equal to 1/2 AB sine C. I think it's also massively important to remember, just because we've now learned this doesn't mean that we need to forget base times height divided by 2. It's so much easier if you've got a perpendicular height to do that. So this is just when we don't have that perpendicular height. Okay, a patchwork bed cover is to be made from 300 pieces of fabric cut into the shape of the triangle shown. Calculate the area of the bed cover in square metres correct to 1 decimal place. So what we've got then is it's in centimetres, and we need 300 of these, and we need to put it into metres. So all I'm going to do, I like to turn it the other way around. Let's put that on. We've got a nice 60-degree angle. Working with some angles is nicer than others, especially if you're doing it without a calculator. As the sine of 60 degrees, as you will see over time, gives us a special angle. So let's put the 60 on. I'm going to write this in metres. So this is going to be 0.12 metres. And this one is going to be 0.15 metres. So if I just define the third length as stated, we really don't massively need to do that, but we can do anyway. So what we're going to have is the following. We're going to have 300 of these. So I need 300 multiplied by, then what we're going to have is 1/2. We're going to have A, which is going to be the 0.12, multiplied by the B, which is 0.15, multiplied by the sine of 60 degrees. You can of course work this out in terms of centimetres and then convert into metres. I just prefer, if we're going to give it in metres, to convert these from the start. So what we're going to have then is the following, and you can do a lot of simplifying with this if you want. 300 times by 0.5 times by 0.12 times by 0.15 times by the sine of 60 degrees. If you're interested, the sine of 60 degrees gives us a special angle, and that is √3/2. So that's what's going in the calculator, and that's going to give me 27 √3/20, which is going to give me 2.338. So we can say 2.338 ... and now we can say 2, 1 decimal place. This will be 2.3, and that will be metres squared, given now to 1 dp. So all I've done is done 300 lots of this once I've converted it into metres. We're told a regular pentagon lies inside a circle of diameter 20 centimetres, with its vertices touching the circle. Calculate the area of the pentagon. So if we think about this, if this is a regular pentagon, we're simply going to find one of these angles, and those angles are going to be 360 divided by 5. 360 divided by 5 means each of these are going to be 72 degrees. If we then consider that all of these are going to be equal, these are the radius or radii of now the circle, as we've got the centre and we've got the vertex touching the circumference. So if we've got a diameter of 20, we've got a radius of 10. So all I would need to do in this particular problem is a quick sketch. So if we go ahead, quick sketch, nice and straightforward, we could put on now that this is going to be the angle. We know that the angle here is going to be 72. So 72 degrees, this is going to be 10, and this is going to be 10. This is a property that we're going to use a lot with our studies, that if you have a radius, it creates an isosceles triangle. So I'm going to have 5 of these, so I'm going to say 5. I've got one here, one here, one here, one here, and one here. So it's going to be 5 multiplied by 1/2, A, which is 10, B, which is 10, and of course you can put 10 squared, multiplied now by the sine of 72 degrees. So if we look at this, that is going to give me 100 over 2, which is going to give me 50, 5 times by 50, 250 sine of 72 degrees. So that is going to give us the area of the pentagon, and we can put this in. So we're going to have 250, and then multiply that by the sine of 72 degrees, and that will give me in total 237.76, and so on and so forth. So I'm going to say 200, so 238, and that will be centimetres squared, and that is given now to the nearest integer, or if you like, 3 significant figures. I'm just rounding as I wish, really, rather than being given, we're not told any level of accuracy, so we'll just look at some different levels of accuracy. Okay, let's now look at finding the area of the shaded region. So what we've now got is a circle. and we've got a sector. So this is a sector and it cuts off a segment. So this part's called a segment. The whole thing is a sector, this is a segment. What I'm going to do is a quick sketch. We're going to have now to find the area of the sector, 2 of the radii, and we've got the angle of 80 degrees. So if I come round, we'll have something looking like that, and it'll come up here. So this is going to be 5, this is going to be 5, and this is going to give me 80 degrees. When we've looked at finding now a portion of a circle, we've simply said that the area is going to be the fraction of what we've got. So we've got 80 of the 360 multiplied by pi r squared. That will give me the area of this sector. We know it's just part of a circle. So we could tidy this up if we wanted. I mean, you can divide both of these, what, by 40? I suppose we could, let's just leave it as it is rather than, I'll put 8 over 36 multiplied by pi multiplied by the radius squared, which is going to give me 25. So that now will give me the area right here. If I think about this, if I cut a line across here, I could find the area of this triangle and simply subtract that away, and that would give me the shaded region. So what I've done is found now, I'm going to write that this is the area. So this is the area of the sector, and I can find the area of the triangle by using exactly what we've just done. We don't even need to do that if we didn't want. We could go ahead and find the perpendicular height by splitting this angle right here and saying it's 40 degrees and using basic right angle trig. It's entirely up to you. I'm going to put in that this is 5, this is 5, and this is going to be 80. So what we can say then is the area of the triangle, and I'm going to call it area of triangle AT. We're going to have 1/2, then we're going to have 5 multiplied by 5 multiplied by the sine of 80 degrees. So that's going to give me now that the area of the triangle is going to be 25, we can write this now as 1/2 multiplied by 25 multiplied by the sine of 80 degrees. So that's what we got. And we could factor this if you really wanted. Often you'll see this in factor form. We don't need to, but I'm simply going to subtract one away from the other. So if we do this, let's put this in a calculator. So we can say now that the area, and I'll call this one R, we will say that that is R. R is going to be equal to the area of the sector minus now the area of the triangle, and that will just give us the shaded bit here. So what we'll do this one here, and let's put this in. So we'll have now 8 times by, and as stated, I would expect, if I was not talking for this, I would tidy it up and make it look a bit nicer. And then we're going to subtract now from this. We're going to have 25 lots now of the sine of 80 degrees, and we're going to divide that by 2. So plugging this in, that will now give me the value, and that is going to give me 5.14. So this is going to be 5.14 centimetres squared, and that's given now to 2 dp. So let's check my rounding on there. That looks pretty good. 5.14 to 2 decimal places, and that gives me the sector. So there we go. We're simply now subtracting that away. So there we have it, looking at finding the area of a triangle when we don't have a perpendicular height. We simply use the formula 1/2 AB sin C.